let's think about what might happen if we had a molecule of butanoyl chloride. So 1, 2, 3, 4 carbons. That's where the but comes in. And then it's a butanoyl chloride. So it's an acyl halide, or it's an acyl chloride. Let me write this down just to give us some practice with namings. This is butanoyl chloride. We saw a couple of videos ago that acyl halides, you just count the main number of carbons. 1, 2, 3, 4 carbons. That's where the butan comes from. And then this is an acyl chloride. So the acyl chloride part, this part, gives us the oil, or I guess you could look at even at the carbonyl. We could even say this whole part over here, we know it's a carboxylic acid derivative. It's an acyl chloride. So that's why we have the oil here and the chloride. So let's think about what would happen if we have a molecule of butanoyl chloride, or if we had a solution, even better, of butanoyl chloride. And for every molecule of butanoyl chloride, we had 2 molecules of dimethylamide, or sorry, dimethylamine. Let me draw that. So dimethyl, so 2 methyl groups. 1, 2, and then we have 1 hydrogen. And then we're going to have 2 molecules of this for every 1 molecule of our butanoyl chloride. So let me copy and paste this. So edit copy and edit paste. So let's think about what would happen in a solution with these reactants in this ratio right here. And just as a bit of a review, this right here is dimethyl. We kind of have a tie for our longest chain attached to the nitrogen. Dimethylamine. You could pick one of these as the longest chain, and then it would actually be N-methylamine. Either one. This is the one that you're more likely to see. But this video isn't about naming. This video is to think about what's likely to happen. So what are we dealing with? We have an amine here, and then we have an acyl chloride. And if we look at our hierarchy of stability that we looked at in the last video, we saw that when an amine reacts, or a carboxylic derivative from an amine, which is an amide, is much more stable than an acyl chloride. This is the least stable. So if we're starting with an acyl chloride, and we have the ingredients for an amide, this reaction will probably end up with amide. So let's see how that we can get there. Well, we know from previous videos when we studied amines that they are pretty good nucleophiles. So they could have a nucleophile attack on this carbonyl carbon right over here. So you can imagine this amine right here, this nitrogen, gives an electron to this carbonyl carbon. This carbonyl carbon can then let go of this electron to this top oxygen over here. It was already hogging it to begin with. And so the next step of our reaction would look like this. What was the butanoyl chloride will now look like 1, 2, 3, 4 carbons. Now you only have a single bond. This oxygen up here now has a negative charge. Since it took an electron from this central carbon right over here, you are still bonded to this chlorine. And actually, let me do that in a different color so we can keep track of it. You are still bonded to this chlorine atom. And then the nitrogen has been bonded. So this bond I'll draw in green because we're giving this green electron to form the bond. And then the rest of the dimethylamine is still over there. Let me do it in that same color. The rest of the dimethylamine. So you have CH3, CH3, and then you just have your hydrogen. And then this nitrogen gave away an electron. So it has a positive charge. Now, the next step of this is chlorine. It's fairly electronegative. It's a not so bad leaving group. It will want to hog this electron that is on this central carbon. So you can imagine in the next step that this oxygen gives back an electron to reform the carbonyl group at the exact same time that this chlorine takes an electron and forms a chloride anion. So the next step in this will look like, so the molecules will now look like you have there 1, 2, 3, 4 carbons. That's one of the bonds to that oxygen, but now you've now formed another bond. That electron was given back to that central atom, and now you have the bond to the nitrogen, this bond right here. And then the nitrogen is bound to 1 methyl group, 2 methyl groups, and a hydrogen. And it had given away an electron, so it has a positive charge. And the chloride anion has been bumped off. the chloride anion, it took an electron from that central carbon. So now it has a negative charge. Now, we still have that other dimethylamine molecule. Or for every one of these, we have two of these. We've only used one of them. So let me bring the other one into the mix. And this one could just be in the mix to make this other, well, this other molecule neutral now. And this could go in either direction. This part right here could go in either direction. This guy's a not so weak, or it's not a bad base. So this guy could give an electron to this hydrogen proton, and then the hydrogen proton's electron, or that hydrogen atom's electron, can be taken back by this nitrogen to make it neutral. And I'll make this go in both directions. So this could go in both directions. So then this molecule over here will look like 1, 2, 3, 4 carbonyl group. And let me color code it the same way, just so we know what parts are which parts. We have this green bond to this nitrogen, which has now lost a proton. It was able to take back an electron, so it is now neutral. It is bonded to 1, 2 methyl groups. This dimethylamine took a hydrogen. So let me draw it over here. So it's nitrogen 1, 2. And then it already had one hydrogen, and now it's gaining another hydrogen. It's gaining this hydrogen right over here. So now it bound to that hydrogen. It gave an electron to get that hydrogen nucleus, so it now has a positive charge. And of course, we can't forget about that chloride anion that's floating around. That chloride anion that's floating around. And these might be attracted to each other. One's positive, one's negative. Form a salt. So what are we left with? And then once again, this is a little bit of practice of naming. We started with an acyl chloride, and we ended with an amide, because we now have this nitrogen group attached. So what is this? This has 1, 2, 3, 4 carbons. So it's butane, but it's an amide. So this part tells us that we're dealing with an amide. That part, right? Butane. It's butanamide. But to specify what type of amide, we see that we have two methyl groups attached to the nitrogen there. So we would call this, let me put another color here. We have 1, 2 methyl groups attached to the nitrogen. So we would call this N, N, dimethyl butanamide. This N lets us, this N, N lets us know that the methyl groups are attached here, as opposed to on the butyl group. I guess we could view it this way. So we end up with NN dimethyl butanamide, which is an amide, one of the most stable carboxylic acid derivatives. And then this right here, this salt, what is this? This right here is dimethyl. This right here is dimethyl. And this is now no longer dimethylamine. We now are a positively charged cation. So this is dimethylammonium. Ammonium. We get that from the fact that we have 4 bonds. We have a positive charge. This is dimethylammonium, and then we have this negative anion. Dimethylammonium chloride. I'll just go to the next line. Dimethylammonium chloride. But I really just wanted to show you a mechanism here of how you could go from a less stable, or one of the least stable carboxylic acid derivatives, to one of the most stable, going from an acyl chloride, which butanoyl chloride was, to an amide.